thought I'd show you a couple problems. I think this chapter 9, is going to take me 3 lecture days as opposed to 2 to complete chapter 9. So we're going to jump right into that and start doing it. The first thing I'm going to do is address something called recoil. So, and that's what I was trying to pull up that movie or video segment for, because there's this problem that basically everybody in Hollywood always does, basically a violation of the laws of physics that virtually every cool movie does. So for instance, if you see Dirty Harry, i.e. Clint Eastwood, shooting someone in the chest with his big 50 caliber gun, right? When he shoots that, he hits the guy in the chest, and then the guy flies back through the wall and stuff like that. That's not at all how that happens, and you'll see why, because we're going to do a recoil calculation and let you see that, in fact, assuming the guy is roughly the same size as Clint Eastwood, if Clint Eastwood was holding a gun big enough to do that to a person, then that would do that same thing to Clint Eastwood, because the recoil is basically exactly the same momentum, pretty close anyways, exactly the same momentum gained by the person that's being shot is the same momentum that's being absorbed by the person doing the shooting. So unless he's like a factor of 10 or a factor of 100 larger than the person who's shooting, which would be horrible, right? It's like a grown-up versus a small child or something, then that's never going to happen. You're never going to, blow a person through an actual wall. So let me start off by showing you one of those calculations, and I'm using some popular data. I'm going to ask you to consider the recoil of an AR-15. So let's say this is example 1. So an AR-15 is a weapon. They call it, they call it a lot of politically charged names, but in fact, it's more or less somewhat of the model of the M16, but they use a lighter round, which in some sense seems like a little better, but also in another sense, it seems like a lot worse. You can debate that all you want. It's not a big deal. That's not what we're talking about here. But the key points that I want to make about the AR-15 is that it does use quite a small round. It uses a .223 Remington, which is basically like a 22 type shell, only it has a lot more bang for the buck. So 22 doesn't have as much water, doesn't have as much actual gunpowder and stuff like that in it. So it actually has a much larger muzzle velocity, especially from the AR. So in fact, you can say that the AR-15, which has a mass of about 6.55 pounds, that's about 2.97 kilograms. So that's the mass of the AR-15. The 227 or the 223, which no one ever writes a 0 in front of, and very few people even write the decimal in front of. The 223 Remington, I had to look these up to remind myself, but basically the 223 Remington, it has a range of masses between 2.27 grams up to, and this is grams, not grains, up to about 5.8 grams. That didn't turn out so good. I'm going to use sort of the middle of the road, which is their 56 grain or 3.56. So the M of the, I'll call it B for bullet, is basically 3.56 grams. Okay. Now that turns out to have a muzzle velocity with this AR-15 of about 993 meters per second. So what recoil is about is actually just about conservation of momentum. So P initial equals the mass of the AR-15, which I'll write as MAR, times the velocity of the AR initially, plus the mass of the bullet, which I wrote as MB, times the velocity of the bullet initially, which I think you can tell if a person's just sitting there holding an AR-15 or even, laying down on the ground and sighting through an AR-15, neither the bullet nor the AR-15 are moving. So that 0 plus 0 is just equal to 0. The final momentum, on the other hand, is got to be the mass of the AR-15, which I'm going to go ahead and write down as 2.97 kilograms, times V of the recoil, that's the velocity of the recoil, plus I'm choosing right as the positive direction, and that's going to be the direction I'm firing the bullet. So that's going to be plus the mass of the bullet, which is 0.00356 kilograms, times the muzzle velocity, which is 993 meters per second. And that's the P final. So you do all that calculation, that's P final. But since the net external force applied to the system, we're literally imagining here, basically the rifle is sitting like this and nothing's applying any force to it. So in principle, it could maybe even have some wheels attached to it or something like that. So it just fly off backwards like that and be very frictionless. So this is sort of an imagined scenario where you're pulling the trigger and just sort of letting go of it and seeing how fast it'll fire backwards at your shoulder. And that's a good measure of how much pain you're going to feel, because basically the momentum of that rifle is going to be applied to your body, and then your body's going to have to apply an impulse force to stop it. And that force you feel can actually be decreased, of course, by increasing the contact time. So if you allow your shoulder to do this a good ways with it while it's shooting, then it's going to be less painful because you're spreading the force over that whole amount of time. Whereas if you stand rigidly without the softness of the muscles and stuff in front of your tissues, then that could actually cause a very severe force and bruise. Of course, also you'll know if you don't hold it tight enough, then you've got this whole velocity coming flying. So if there's some gap between your shoulder, then that would be a problem, because then it's going to come fast and hit you. Okay, so all we have to do is set these two equal to each other. We're going to say P initial is equal to P final, and that gives me 0 is equal to 2.97 is equal to 2.97 kilograms times V recoil minus, or actually this one will be the plus. Now I'm going to do this multiplication, which would be 0.00356 times 993, and you get 3.535. And that's actually, one extra sig fig. So 535, that's actually one extra sig fig. So I'm going to put a 1 here. And now it's 2 extra sig figs. And that's kilograms meters per second. So I can solve for VRC. And since I said the bullet was going this way, and I'm treating this as the positive x-axis, maybe this would be the positive y-axis, then you're obviously going to see why I get a negative here. So I'm going to take that 3.535, and I'm actually going to now divide that by 2.97. And that gives me basically 1.1903 meters per second negative. Okay, so you see that velocity is not huge, it's on the order of like 3 miles per hour, but a 6.5 pound thing coming at you at 3 miles per hour is still pretty painful, right? So it definitely has some kick. It doesn't have nearly as much kick as you got. In fact, what I was most impressed about with the Ar-15 when firing it is basically how loud it is. It's got a really loud report, unless you, of course, do something to muzzle that. But anyway, so that's a typical recoil. And that's quote unquote a gun that people are complaining about as a quote unquote assault rifle, which is not what the AR stands for, by the way. But you can see that still, this is not a force that's going to push a grown man through a wall. If you take a something like a 357 or a 50 caliber handgun, that's clearly not going to do it either. Okay, so that's what they get wrong in a lot of movies. But that's just one simple problem. That's a typical recoil problem, and that is what gives you recoil. And if you're not holding the weapon properly when you fire it, you will, there will be pain. There's been people that are sort of really loosely holding a handgun, and that'll, especially if it's like an automatic one, like a Uzi or something like that. They recently had several years ago, a guy was training a young girl how to shoot an Uzi, and it got out of their hands and ended up killing the instructor, which is really a horrible incident. But that's just another fact of the kickback, and combine that with the fact that the kickback is strong. The guy was probably not in the best position to prevent an accident, and the fact that the girl was the young child was actually quite weak compared to, you know, what was expected. Yeah, that was just a series of unfortunate events. But in general, recoils are not that high, so you shouldn't have problems like that. Any questions on that one? All right, so I'm trying my best not to get any political with anything, but trying to give you some real life examples that are relevant. Let's do example 2. And in this example, I'm going to use a conservation of momentum situation, and I'm going to basically try to find some general expressions for conservation of momentum. So what I'm going to do is do a one-dimensional head-on elastic collision. Okay, so I'm really examining one-dimensional. So this is literally a head-on collision, and it not only conserves momentum, it's elastic, so it conserves kinetic energy as well. So what we might say is, since it's one-dimensional, I don't have to worry about the vectorness of it other than the plus or minus sign indicating positive direction or negative direction. But what I will get is the mass of the first object, which I'm calling it mass sub A, times the velocity of the first object, v sub A, plus the mass of the second object, m sub B, times the velocity of the second object, v sub B. And this is all before the collision. So this is P initial. Now, if momentum is conserved, which means the net force on the system is 0, then this has to be equal to the final momentum. So that final momentum would be mass of A times what I'm going to call VA prime. Okay, so the prime indicates the final velocity, and that's the only difference between the two. Plus, I'll have a mass B times the final velocity B. Okay. Now, this is an equation. Your book gives you sort of the equivalent of one, and it actually numbers it, if I remember correctly. Let me double check, see if that's the case. Because remember, all numbered equations are obviously allowed to be copied on your equation sheet. And I know I saw it earlier. Where's that? Oh, yeah. This was equation 9-3. So if you look in your book on page 217, you'll see equation 9-3. I use different notation because I was drawing off the top of my head, but that's essentially the same equation. So you can include that on your equation sheet. Now, if momentum is conserved, which is more likely to happen than kinetic energy conserved, that just requires the net force on the system being equal to 0 or so small that you can pretend it's equal to 0. The other aspect is, what about the elastic collision? And in that case, you have 1/2 mass of object A times the initial velocity of object A squared, plus 1/2 the mass of object B times the velocity of object B initially squared. Again, if the kinetic energy initial is equal to the kinetic energy final, that's the kinetic energy initial. So now I'll write it equal to 1/2 MA VA prime squared plus 1/2 MB VB prime squared again. And that's another equation. That's conservation of kinetic energy. And your book probably does that one too, and labels it. Let me see if I can find it. Yes, it labeled that one 9-7. So again, they'll use different notations, but it's essentially the same equation. And it's not like a copyrighted thing or anything like that. It's just the laws of physics. So with these two, we can actually do a lot of stuff. Okay. In fact, I can start making some really wise choices by first taking 9-3 and rewriting it in another way. So what I'm going to do is I'm going to write M sub A, and this comes from years of experience of knowing how to work algebraically with just pure symbols. What we're going on here is we're assuming that we know the masses of the two objects and we knew the two initial velocities. Ideally, what we'd like to solve for is the two final velocities. Well, I have two unknowns and two equations, so I should be able to do that. And in fact, we can even do that in this nice algebraic form, which is what I'm doing now. So the trick that I've learned over time is that I can take this first equation and just make it NMA times VA minus VA prime. And that might not seem very helpful, but you'll see why in a second that it is. And then I'll do the same thing with the other side, but with MB. And when I do that, I'll write MB. Now notice on this side, the prime one is positive. So I now have to do VB prime minus VB. Okay, So that'll be a new equation. I will call this equation 1. Okay. And that's just so I can refer to it later and summons it later. Now I'd like to do something else with 9-7. And this is where it becomes smart, because I have a VA squared here. And I can pull the VA here just like this. And then I have a VA prime squared. And then I can use a little trick about factoring. Notice there's a common factor of 1/2 though. So that's the first thing we're going to make use of. We're going to get rid of that common factor of 1/2. I'm now going to write MA times VA squared minus VA prime squared. See how that sort of looks like this equation? And then I'm going to say that's equal to the VB prime has to come first on this one too. So I'll say MB VB prime squared minus VB squared. So that's nice, but not quite as nice as I'd like. In fact, what I'd really like to do is now rejigger this so that I've actually got a something that's useful. So what I'm going to do is factor this, and I'm going to say M sub A VA minus VA prime times VA plus VA prime is equal to M sub B, VB prime minus VB times VB prime plus VB. See how that's equivalent to that? Remember that from factoring? I'm going to call this equation 2. And now I'm going to divide equation 2 by equation 1. Okay. And I think you can see already what happens when I do that. That's really nice because I've got a common factor of MA VA minus VA prime. Boom, boom. So all I'm left with now is VA plus VA prime is equal to, again, this VMB is there and this VB minus VB prime minus VB is there. So those two are going to cancel out. And this is just going to leave me VB prime plus VB. Now that's not necessarily all that helpful of a form for me, but with a little bit of work, I can actually manipulate it a little bit and write something kind of helpful. So what I can do is write the change in initial velocities, or the difference in the initial velocities and how they're related to the difference in the final velocities. So I could, for instance, take this and say VA minus VB is equal to, so this came over here, that became negative. This comes over here, that comes negative. So that's VB prime minus VA prime. So that's one thing I could do. And that's actually pretty close, but really the way I like to write it is VA minus VB is equal to negative VA prime minus VB prime. Then everything's in the same order, and I'll call that equation 3. Okay, so that's a really nice expression, and it's so valuable of expression that your book took the time to actually label it, and they called it equation 9-8. Again, I use different notation, but it's essentially the same equation because everybody knows this trick. So now that we know that trick, we can actually use these to solve problems. So let's look at example. Let's look at example 3. So this is the generic example. Example 2 is generic, and just gave us a nice new equation to use. And I'm going to circle that equation because that's super valuable. And we haven't made any assumptions other than it's one-dimensional, head-on. So 1D, which also implies head-on or basically not happening at all. You can completely bypass each other, and elastic. So those are the necessary conditions for that equation to be valid. So now I'm going to look at example 3, and let's do this one in blue because I'm getting sick of looking at my black pen. So let's do, actually, let's do it on another sheet of paper because that's not very much room left. So now I'm going to do example 3. And in this case, I'm going to imagine basically 2 pool balls. And we're going to say 2 pool balls of identical mass MA equals MB, it equals just plain M, collide. A, VA prime is question mark, and VB prime is question mark. And then part B, what is VA prime and VB prime? That's not a sum, that means and, like ampersand. VB prime if MA is much, much greater than MB. Actually, I won't do that one right now. I'll just do VB and V. Yeah, I'll do that for right now. Let's scratch that one. I want to save that for a later collision. You can still do it if you wanted to, but it's just not, I think I don't want to spend all that time doing that when I'm planning on doing that for a more severe problem a little bit later. Okay, so we'll just say that, and obviously part A makes no sense. But what we have is we have these equations. We have VA minus VB is equal to actually I should say negative. It's actually equal to negative VA prime minus VA, or excuse me, VB prime. So that's an equation we can make use of. And because I actually have two equal mass pull balls, then we can actually make use of the momentum equation, which was MA-VA plus MB-VB equals MA-VA prime plus MB-VB prime, to just say, wait a second, VA plus VB is equal to VA prime plus VB prime, right? So that's one thing we can use. That's just because all the MAs and MBs are equal to each other. So I can just treat them all as M, and M and divide through by it, and I got that. We can also use the kinetic energy, which was 1/2 MA-VA squared plus 1/2 MB-VB squared is equal to 1/2 MA-VA prime squared plus 1/2 MA-VB, or actually it's supposed to be VB and MB. Don't know why I said A again. MB-VB prime squared. Again, that gives me, because of the mass and the 1/2 all being the same, I can just say VA squared plus VB squared is equal to VA prime squared plus VB prime squared, right? Well, this sort of ultimately leads me back to exactly that expression. In fact, you can see that VA, if I refactor this again, I could say VA squared minus VA prime squared is equal to VB prime squared minus VB prime, or excuse me, minus VA prime. No, it's just plain VB, sorry about that. VB squared. Okay, you can now factor that, and you'd see immediately that I'd get a VA plus VB that could cancel out and stuff like that. Well, when you do that, life gets really nice. So I have a VA minus VB. I'm going to say VA minus VA prime times VA plus VB prime, or excuse me, plus VA prime. Sorry about that. A lot of subscripts to talk about here. VB prime minus VB, VB prime plus VB. Now you can see I might be able to combine these in such a way that I can do something useful. So for instance, this VB, VA plus VB, and this VA plus VB, I could actually combine them in such a way that things disappear. So for instance, I can take the VA minus VB. So I'll say VA minus VB equals negative VA prime minus VB prime, like that. And I can combine that with the VA plus VB equals VA prime plus VB prime. So notice this is just this equation right here. That's that equation. And then this is just basically that first equation, which I could have got from this and combining those. So if I add these, I end up getting 2VA is equal to, notice the VA prime is negative and this one's positive, so they'll cancel out. And this one's going to be positive, so I add together to get VB prime. So we've already found VB prime is actually equal to VA. So that's one of our results. We know that if the masses are equal, then the pool ball that's moving initially, say with a velocity VA, will hit the other one, and the other one will move off with the velocity equal to it. Okay. Now, if we use this to put in another equation, for instance, we can put this in, say, this equation right here, then what we'll get is VA minus VB, those are both we know, equals negative VA prime. So I'm distributing that negative there. And this will become positive. So that's plus VA, because VB prime is VA. So now from this, I could actually just say VA and VA cancel each other out. And I'd see that VB is equal to negative VA prime, or ultimately VA prime is equal to negative VB. So this is another result. So if you have, for instance, a ball moving with a velocity of 5 meters per second, say, and another ball moving with a velocity of, say, negative 3 meters per second, then what's going to happen is, boom, they collide. And then after the fact, you've got VA is going to be leaving with a velocity of negative 3 meters per second. And that's why I'm showing the arrow this way, is because it's negative. And in fact, VB, which was the white ball, will now be moving at 5 meters per second. Okay. Any questions on that?
Could you zoom in or put the paper?
Yeah, let me do it this way. Let me first off get a better focus for this close up. And you see, okay, well, we actually did all that part. I'm going to go to, yeah, I forgot that was the same thing. So let me get a better focus again. So two pool balls of identical mass, MA equals MB equals M, collide. I want to know the final velocities, VA prime and VB prime, assuming I know VA and VB. So I come up with all these equations, and some of it I was actually trying to feel my way around and figure out what I could do to get the right answer. But ultimately, all I really needed was the conservation of momentum equation combined with that equation, what your book called, 9-8. That's really all I needed. So some of this was extra work that I didn't need. I was in the process of trying to figure out how to best solve it. So ultimately what I did was use that equation 9-8 and my conservation of momentum equation, and was able to get that the VB prime was equal to VA. And then I plugged that back into my equation 9-8, which is what I did here. And when I did that, I got VB is equal to negative VA prime. So ultimately what that means, is maybe you're hitting a, let's say a green ball towards a white ball. Obviously that's the opposite of pool, but anyways, you're hitting it at 5 meters per second and it's coming towards this one at 3 meters per second. They're going to collide. And then all of a sudden this green ball is going to be moving at -3 this way. And the cue ball is going to be moving at +5 that way, as if they just sort of traded momenta with each other. And that's the origins, if you will, of Newton's cradle. You actually see a little bit better of it in a few, but that is sort of what happens with Newton's cradle. Only with Newton's cradle, you normally just pick up one side, let it go, and it comes down and slams into the other one and then lifts up. So that would be the case where the initial velocity, one of them was just initially sitting still, and that's the problem I'm going to attack next. So anybody have any questions on that? I'm sorry about the quality. Like I said, I started uploading that video with more than enough time, but it's clearly not paying off. All right, so let's attack another problem now. So we just did one where basically pool balls that had equal mass, whereas that initial example 2 was a generic case where you didn't necessarily know anything about the masses being equivalent. So now what I'm going to do is consider 2 unequal masses, but I'm going to consider the initial case being the second object, MB, it has a velocity of 0. So let's do that one now. So let's say example 4. So example 4, we have unequal masses collide head on, and that actually is sufficient to say it's one-dimensional, by the way, such that one is initially sitting still. So what that means is VB is equal to 0. I want to find, here's part A. I want to find VA prime. I want to find VB prime. And in part B, I'd like to find VA prime and VB prime if MA is much greater than MB. And then part C, I'd like to find VA prime and VB prime if MB is much greater than MA. So obviously when you're dealing with collisions, things can get really morbid if you think of the physical applications. So we'll try not to say that, but you're just thinking of in the case of these large masses is, you know, motor vehicle on human or motor vehicle on motorcycle or something terrible like that. So just be advised, that's why I'm not talking much about applications, because these are, you know, potentially sad things. So we'll just attack it as if it's a physics problem and pay no attention to the applications initially, in some sense. Okay, so let's take the initial masses. What we have, if I write out the potential or the conservation of momentum, I have MA VA. Now remember, the mass B is not moving initially, so it has no momentum. And I'm going to say that's equal to MB VB prime plus MA VA prime. And I don't know why I wrote them in a different order, but I did, because I'm a goober. Okay, so that's one equation we can make use of. And in fact, I'm going to try to get it in a form like I did before. I'm going to say MA times VA minus VA prime. And that's going to be equal to, so I've gotten rid of that term and that term, that's going to be equal to MB VB prime. So that's one of my equations I can make use of. Let's call that equation 1. Okay. And now I'm going to take conservation of kinetic energy. So 1/2 ma/va squared is equal to 1/2 ma/va prime squared, not to be confused with 12, plus 1/2 mb/vb prime squared, again, not to be confused with 12. And in this case, I can actually try to simplify it if I want. And in this case, I'm going to get ma times va squared minus va prime squared. And that's just going to be equal to mbvb prime squared. So this is going to be equation 2. So I can do 1 divided by, or actually 2 divided by 1, but I'm going to write 2 in a very special way. I'm going to write it like I did before. I'm going to say ma times va minus va prime times va plus v a prime is equal to mb vb prime squared. So that's equation 2. Equation 1 is going to be ma va minus va prime, and that's equal to mb vb prime. Excuse me, just plain vb prime. Okay. So now if I actually divide them, which is what I'm advertising here, that's what I said, I'm going to divide 2 by 1. Then what I'm going to get is, you notice this and this cancel out, this and this cancel out. I get VA plus VA prime is equal to, on this side, notice this cancels out. And in fact, one of these cancel out. So I'm just left with VB prime. I'll call that equation 3. Okay. So now all I need to do is I might rewrite this. Let's rewrite this, in fact, to let's eliminate VA prime. So I'm going to say VA prime is actually equal to VB prime minus VA, because I know VA. And if I can put this in something that just has VB prime in it and eliminate VA, then I can solve it. So again, this is another version of equation 3, which I'll call 3 prime, just to make sure I can still label it. Now, in order to go about solving this, I'm going to again use a nice little trick. I am going to go ahead and take this and plug it into another equation. And what I'm going to do is actually plug it into, let's see, I could use that. I could use this. Yeah, I'm going to go ahead and plug it into my momentum equation. So my momentum equation was this thing right here. So I'm going to plug 3 prime into, in this case, I'm going to plug it into 1. When I do that, I'm going to say M sub A times V sub A minus, now I've got to write VA prime. See, that's what's right there. So VA prime, I'm going to say, turn this into a square bracket, turn this into a parenthesis, and I'm going to say VB prime minus VA. And then on the right-hand side from this, I got just plain MB VB prime. So this becomes MAVA minus MAVB prime. And then minus and minus becomes plus. So I'll say plus MAVA equals MB VB prime. Now you see that I only have one unknown, and that is in fact the VB prime. And in fact, I have 2MA times VA. So I have 2MA times VA is equal to, if I pull the VB over here, I get MA plus MB times VB prime. So ultimately, I now know that VB prime looks a lot like our Atwood machine. VB prime looks like the tension of the Atwood machine. That's 2 times mass A over mass A plus mass B times the initial velocity of VA. Remember, the tension in the Atwood machine was actually and all that times just plain G. So it looks like it's missing an extra M, but that wouldn't work anyways with the unit. So that's why I'm using this, just to help you jog your memory. I do not think your book actually derives this and gives it an equation number. Oh, it does derive it, but it did not give you an equation number. Okay. So it gets the same result I did. Now we can use VB prime to figure out what VA prime is. So VA prime, we found, was in fact from equation 3 prime was equal to VB prime minus VA. So what that's going to be is 2MA over MA plus MB. In other words, I'm going to get a common denominator. I've got a VA multiplied in the VB prime right there. So I'm just going to pull that off to the side and write VA. But over here, that'll be a 1. So it'll be this times VA minus 1. But to get a common denominator, that means I have to do minus MA minus MB. And you can see the 2MA minus MA is just going to become MA. And then there'll be MA minus MB. And lo and behold, that looks just like the acceleration for the Atwood machine. So ultimately, I get VA prime is equal to MA minus MB over MA plus MB. And notice that is exactly the Atwood machine, except instead of G, instead of G, you've got VA. Any questions on that? Now, when we do this, we should check and make sure it makes sense. For instance, remember, we did do the case of the masses being equal. Well, if the masses were equal, I'd have M over M plus M. That'd be 2M over 2M. That would just be VB is equal to VA. VB prime is equal to VA, which is exactly what I got when the masses were equal. And then what about VA prime? Well, if these were equal, then MA minus MB would be 0, right? And we'd get VA prime would just come to a stop. MA minus MB, yeah, that makes sense. Okay. Yeah, and I think I might not have addressed that earlier. Got that right, got that right. Am I using the right problem? That looks fine, that looks fine, okay. Okay, all right, so now let's investigate the part B and part C. So I'm gonna need these velocities to make sense of what I got. So I'm gonna go ahead and do that. Oh, I remember what I meant when I was comparing these. If you remember, this is the case where VB is equal to 0. So if MA equals MB, VB and E equals 0 would give VA prime equals 0, which is exactly what we got when MA was equal to MB. Sorry about that. I phased out a second and thought I might have been misremembering one of the problems I worked, but I wasn't. I was actually doing a little better than I thought. The Alzheimer is creeping in very slowly, hopefully. All right, so now that I have these results, what I'd like to do is figure out part B and part C. So part B, I was given the task of finding out what VA prime and VB prime were equal to if, as I stated it before, MA is much greater than MB. So in other words, this is a high-speed vehicle, or excuse me, a large mass vehicle running into something low mass, or you could think like a Mack truck running into a fly. Okay, that's a little less horrible and painful. So I mean, obviously for everybody but the bug. So anyways, if I do that, then I'd say VA, which is the mass of the Mack truck after the, or excuse me, the velocity of the Mack truck after the collision, that's going to be equal to the limit as, let's say, one way you could look at it is you could say that MB over MA approaches 0. That's one way of looking at it. Or you can just say MA is way bigger than MB. But either way, the VA prime was MA minus MB over MA plus MB times VA. Okay. So you see what's going to happen here. If the MB is much, much smaller than the MA, or the MA is much, much larger, then having a million minus 0.01 is still a million, and having a million plus 0.01 is still essentially a million. So I'm basically going to get the speed of the Mack truck not changing. Okay, and you'd expect that, right? You don't expect the Mack truck to slow down because it ran into a fly. Now the VB prime, the poor fly, in other words, let's see what it's going to do. I think y'all have an idea because you've probably at least driven with a regular car and ran into a bug. So VB is going to be equal to the limit again as MB over MA approaches 0. So that's, again, if I multiplied by 1 over MA on top and bottom, then I'd still be multiplying by 1. And this would become 1 minus MB over MA. And this would become 1 plus MB over NA. So I'd get 1 minus a small number and 1 plus a small number. So that's clearly 1 over 1 times VA. So that's what I mean by writing it like this. Now, in this case, we got 2 times the mass of A, the Mack truck, divided by the sum of the mass of the Mack truck plus the fly, and all that times VA. Well, I think you can see what happens if MA is really, really large. You can sort of ignore this MB, or you could just multiply by MA over 1 over MA. And obviously this is going to become 2 VA over 1 plus MB over MA. So 2 over 1 plus 0 is just 2. So this is actually going to leave with about 2 times the velocity of the truck. So if it wasn't for, you know, splattering and getting stuck, what would happen is the fly would be sitting in the air, and then a Mack truck would run into it at 60 miles per hour. If the body of the poor fly was structurally sound enough, it would bounce off at 120 miles per hour. So that's what happens when something really massive hits something really small. Now let's look at what happens when something really small hits something really massive. So this could be like, for instance, you run into a huge bridge abutment or something like that. Obviously, you don't want to do that. That's not a good scenario, but that's what we're talking about here. So in this case, I want to know VA prime question mark and VB prime question mark if MB is much, much greater than MA. Okay. So when I do this, I'm going to say, well, I know what VA prime was. VA prime was equal to MA minus MB over MA plus MB times VA. Whoa, evidently I want to write parallel there instead of V. So I'm going to take the limit again, and this time it's going to be as, I don't know why I underlined it. This time it's going to be as MA over MB approaches 0. Okay, so in this case, you divide top and bottom by MB. This would become MA over MB. This would just become 1. This would be MA over MB. This would just become 1. And you'd see that I get negative 1 over 1. So I get, in fact, negative VA. So this is sort of like my story I told you about when I was running at the NC State track. I ran into accidentally a very large football player who was running really fast, and I bounced off of him like nothing. Okay. And I'm a big guy. This guy was way bigger than me. But what that says is basically you're going to hit this thing and bounce back with exactly the same speed. This will come in handy later when we try to imagine molecules or atoms running into the wall of a container. When a molecule hits a container, that's an elastic collision, because, you know, what other forces could be smaller than that could cause the sides of the container to, you know, grip the atom or molecule. So it's going to be an elastic collision. And if it comes in with a velocity, a horizontal component of velocity VA, then it's going to bounce off that wall with a velocity of negative VA, at least in the X component. Now let's do a VB prime. And you might guess what this is. What do you think is going to happen to a big bridge abutment when I hit it with my bike? Little or nothing, right? So again, this is MA over MB approaching 0, but in this case, it's 2MA over MA plus MB times VA. So again, if I divided by MA, I'd get 2, or excuse me, if I divided by MB, I would get 2 MA over MB. And then I'd get, of course, this would just be MA over MB plus 1. So essentially what I would get is 2 over 1 are, actually in this case, no. I just get a, yeah, that one I got a negative VA. This one I just get plain 0. Because notice this becomes MA over MB. This is approaching 0. And this one, on the other hand, is approaching 1 plus 0. So it's just going to be 0. In other words, the abutment is not going to move as we expected. Any questions on that? There's actually a neat book called, it's by a guy by the last name of Jewett, Jewitt, and it's called, what is it? Magic Begins with a P or something like that. And it's basically all these neat little physics concepts. And one of them is you have a scenario in which you're riding down the road in a car or a truck, whatever, doesn't matter, right? And you have a choice basically to run head on into an identical car going the exact same speed. So this is M, and this is M, and this is V, and this is V. Or you could turn and run into a bridge abutment or something immovable. Okay, and they ask you, which do you do? Well, you can see what happens from conservation of momentum is that the total momentum of this system before is MV minus MV, so it's actually equals 0. So P initial equals 0. That means P final is also equal to 0. So those two cars are going to be bunched up together like this, moving at velocity equals 0. Well, that's exactly what's going to happen when you hit an immovable object, is you're going to come to an instant stop. So really there's no choice. You just need to hang your crap up and call it a day. So that's a, yeah, magic begins with a P, or physics begins with an M, magic, myth, or mystery, something like that. It's an excellent book. I highly recommend it. And it's magic, myth, or mystery. Another one is The Flying Circus of Physics. That has a lot of cool concepts in it as well. But yeah, this is kind of a neat issue. If you're ever faced with that, then obviously you want to run in the ditch instead, right? You don't want to face down a really large tree or an object that's, you know, comparable to you in size. It'd be best if you just run off into the ditch and hope for the best. Any questions on that? All right, so that's really what conservation of momentum is all about, and conservation of energy is all about. Really all we have left is to sort of apply this in various cases, which your book does some nice examples of. For instance, it does a nuclear collision. You can also imagine, for instance, a ballistic pendulum. A ballistic pendulum is basically a scenario where you have, say, a ceiling like this, and then you have two ropes that come down and are connected with a very massive block. Say mass is equal to on the order of 100 kilograms or something god awful like that. And then you shoot an itty bitty bullet, mass M, moving at like 1,000 meters per second. I'll say on the order of that. And this will be on the order of, 1 gram. What'll happen is this will be embedded in there. And you'll get basically the bullet and the object. Here I've got P initial is just equal to little m times big V, which is that right there. And then here I've got P is equal to little m plus big M times V block initial. Okay, and then the third step, this is P final, by the way. Then the third step is this block has now swung upward and has gone to a height H. So now we say, in this case, the energy is 1/2 M plus M VB initial squared. And that's E total. In other words, we're doing UI plus KI equals UI, U final plus K final, ignoring other types of loss of energy. But once the bullet has embedded into this, and we use conservation of momentum to find out what that is, then there's no more energy loss. So it's actually okay to say the total energy is just going to be the kinetic energy of the block. Well, this is set up so that the kinetic energy of the block can be converted to potential energy. So we're now going to say, well, the energy total here is equal to M plus M times G times H. So with all that, we should be able to solve for the initial velocity of the bullet. So I'm going to say M plus M GH is equal to 1/2 M plus M VBI squared. Obviously, the M plus M's cancel out, but what I do find is that VBI squared is equal to 2GH. And now I can use conservation of momentum to say that MV is equal to M plus M times the square root of 2GH. And finally, I can find out that the muzzle velocity of the round for that gun, in other words, is in fact equal to M plus M times the square root of 2GH over the mass of the bullet. And that's actually how you solve a ballistic pendulum problem. It's called ballistic pendulum. So this is a way, for instance, that you could actually determine the muzzle velocity of a gun. Obviously, it's a little dangerous because if you want to shoot a gun at a big heavy object, there's some probability that the bullet might like sort of bounce off or something like that. So if you use steel, that might be a real problem. But if you used a big hunk of wood, that might be a little better issue because it's less likely to come through it. But then you get to the issue where you're going to fly all the way through and shoot your neighbor by accident, and the police will come get you for that. They're not cool with you shooting somebody even by accident. So, but that is a way you can do it. They also use other ways. You've probably seen CSI. They'll shoot it into some gelatinous material that's supposed to represent human meat or human muscle and bone, or you can shoot it into a vat of water and film it and see what that does. And they've got that based on experimental stuff, all sorts of cool stuff. But this is one that comes just from pure theory, and it's something you should be able to solve at the drop of a hat. Now, the next thing that we're really shooting for is really conservation of momentum in more than one dimension. We just finished doing in one dimension with head-on collisions and stuff like that, and that was really nice. But what happens when we have two-dimensional motion. And to make it a little simpler, we're going to consider only the case where one of the objects is sitting perfectly still. Okay, so and you can always use a shift in coordinate system such that this is true. So you're not really losing any loss of generalness. My last example was technically that should have been example 5. So this will be example 6. So example 6, we're going to imagine a object of mass m sub a, let's say. Okay, it's moving to the right with a velocity of v sub a, and it's going to in fact run into an object of mass m sub b that's sitting perfectly still. And what I'm going to do is I'm going to assume this is the positive x-axis and this is the positive y-axis. So after the collision, which I'll draw in red, after the collision, we're going to expect m sub a to fly off at this velocity, which I'm going to call VA prime. And that's a dot, 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 like along there. And of course, that's theta a prime. And then mass m sub b is going to fly off maybe this way. And this is mass m sub b, and that's velocity v sub b prime. And this, of course, would be theta b prime. Now, you can see there's a lot of unknowns here. Even if I knew this mass and this velocity, and the fact that this is 0, I still have this unknown, that unknown, that unknown. So there's 4 unknowns. So that's like a really a holy grail type problem. What I could do though is, let's assume we know these 2, then I just got 2 equations and 2 unknowns. So let's say this particular guy, has a angle of 45 degrees, and let's say this also has an angle of 45.0 degrees. Okay, and in fact, it's technically a negative 45 degrees. But anyways, let's say that VA also is equal to 3.00 meters per second. And we already knew that VB was initially 0. And we're going to go on the assumption that MA is equal to MB. Well, lowercase ma is equal to lowercase mb is equal to just plain m. So it really doesn't matter too much. So what I'm going to have is P initial is equal to P final, because the net external force acting on it should be roughly 0. Obviously, there's friction and stuff if these are really pool balls, which is what I'm imagining since I took the masses to be the same. There's friction and all sorts of forces like that, but they're probably fairly small compared to the collision forces. So if I take this, then what I'm going to find is the initial momentum is just ma times 3.00 meters per second, and that's in the I-hat direction. Okay, now the MA is not really going to matter because you'll see it'll divide out in a second. But since this was all going in the positive X direction, it's initially one-dimensional. So that makes life really easy. Now, after the collision, the P final is going to be, again, I'm going to actually, since we already decided that MA equals MB equals M, I'm just going to call that M so it'll make it a little easier. Now I'm going to realize that this guy has a velocity VA prime. So that's going to be M times VA prime times the X coordinate would be cosine theta A prime. And that'll be in the I-hat direction, plus M VA prime sine theta A prime in the J-hat direction. Now I've got this one that's going to be plus M VB prime cosine theta B prime in the I-hat direction. And then notice I'm just using my understanding of the signs instead of the signs of the angles. And this, of course, is going to have a negative y component. So I'll say negative m VB prime times the sine of theta B prime j hat direction. So on this side, I have an actual x component, and this side I have an x component and a y component. So the x components alone are going to give me the following. Notice there's a common factor of m in here. I'll do it this way. There's a common factor of m right here and right here and right here. So I can cancel that out by dividing through, and I'm going to get, in fact, 3.00 meters per second is equal to, now these are 45 degrees, so the cosine's easy peasy. It's root 2 over 2. So I'm going to say square root 2 over 2 VA prime plus square root 2 over 2 VB prime. So that's my x component. So I've now taken care of this term and this term. Now my y component gives me 0 is equal to, now I've got an m and an m, they're common to each other, but they're both equal to 0. So I don't need to write them at all. I'm going to say VA prime root 2 over 2 minus VB prime root 2 over 2, because the sine of 45 also happens to be root 2 over 2. Okay. So you now can see, hey, wait a second, this is the absolute same as that one, except it's different by a sign. So if I add those two together, then I will get 3 plus 0 gives me 3.00 meters per second is equal to, now I've got square root of 2 over 2 plus the square root of 2 over 2. That's just the square root of 2. So it's equal to the square root of 2 times VA prime. So I now have VA prime is equal to 3.00 meters per second divided by 1.414 roughly. So 3 divided by, I'm going to actually write square root of 2. And that's 2.1213 meters per second. Obviously, I put in 3 sig figs, so these two are extras. So I now have one of my velocities, VA prime, is equal to that. Now my other velocity, since I know VA prime, I can just plug it into this one. And you can tell just from the symmetry of it, notice that these two basically say that VA prime is equal to VB prime. So VB prime is actually going to be 2.1213 again meters per second, which I should really highlight with a different color. So that's how you can actually solve a two-dimensional projectile motion problem if you're lucky enough for them to give you too much stuff. Now, sometimes the problem is they can give you so much stuff that it's actually inconsistent. Like if I would have just made up these angles instead of remembering the problem in the textbook, then there's a high probability that something bad could have gone wrong because I might have made an equation that's impossible to solve. But you can see, as long as you're just dealing with momentum, you can only have two unknowns. It could be maybe the two angles, or it could be the two velocities, or it could be one of the velocities and one of the angles. But if you add to that conservation of kinetic energy, then you got 3 equations. So you could actually have 3 unknowns, and you could solve that. That's sort of the toughest of the tough. And with that, you can look for examples. Now, the neat thing that comes from this is all this conservation of momentum stuff can be exactly repeated without using conservation of momentum. It turns out that the equivalent thing to conservation of momentum is basically the center of mass. So it turns out when momentum is conserved for a system, the summation of force is equal to 0. That means delta P over delta T is equal to 0. So P equals a constant. Okay, then that means the momentum of the center of mass of the system is going to just constantly move at a set velocity. In other words, with a set magnitude and direction. So if you can figure out where the center of mass is, you can just always use that center of mass as if it's moving at a uniform velocity, and then work backwards to figure out the positions of the two particles. So in order to do that, we need to understand what center of mass is. And I think it's pretty easy if you think in terms of trying to balance something. So let's take a uniform stick, not like a bat, because a bat would be like heavy on one end and light on the other. You take like a uniform stick, and let's say, you know, if the stick's 1 meter, you'd want to balance it at the 50 centimeter mark, right? And you also know that if I hang a mass over here, so let's say this is 50 centimeters, let's say this is 30 centimeters, so that's 20 centimeters there. If I hang a mass of, say, 10 kilograms here, then where would I need to hang a 20 kilogram mass to balance it? Anybody know?
Twice as far.
Now I'm trying to balance 10 with a 20, so that's actually twice as heavy. So do you want to go twice as far away?
Yeah.
Yeah, you want to go half, right? So this one was 20 away, so I want to go to 40. Boom. And the reason why is this is 10 centimeters and this is 20 kilograms. So if you multiply 20 kilograms, which you might want to multiply by G, but you don't really have to. As you can see, that unit's going to cancel out anyways. And then multiply that by 10, let's say centimeters, then you're going to ultimately get 20 times 10, that's 200 times 19.6, that's 1,960. Now this one's 20 times 10, so that's 20 centimeters times 10 times 9.8. Well, that's 200 times 19 points. So you see, again, that's 1,960. So that's actually how you balance it. So it turns out that M times the distance is something relevant. And in fact, the formula for the X center of mass is actually equal to, if you have assembly of masses, it's MA times the center of mass of A plus MB times the center of mass of B plus dot, dot, dot onto MN times XN. In other words, if you have N particles, it would be mass times distance plus mass times distance plus mass times distance. Now that just gives you like all the forces acting on it, right? If I multiply it by G, it'd give you all the forces acting on it. What I want is something measured in units of like centimeters or meters. So I got to get rid of those masses. So the most reasonable thing to divide by is MA plus MB plus dot, dot, dot plus MN. And in fact, that turns out to be exactly the right formula. So that's the center of mass formula for discrete items along some kind of plank. Basically, what you'd want to do is do all this, and then you could put your finger there. So in this case, I said 10 times 30. So we go using this formula, 10 times 20. Plus the other one was actually, let's call this 0 for this coordinate system and just find out where our finger is going to be. So instead of 10 times 30, I'm going to say that's 10 times 0 right there, because I put the coordinate system there. And then I'm going to say plus, now I've got 30 all the way to 40. That's a difference of, ooh, that's not supposed to be 40. I think y'all know that's supposed to be 60. And I think you know that that is 20 times 30, because clearly I'd be 30 centimeters away. And then I'm going to divide it by the sum of those two masses, which would be 30. Well, I get 20 times 30 divided by 30. That's just going to be 20. And in fact, that's supposed to be what the center of that is, which if that was 40, that would make a little bit more sense. But it's going to be 20 centimeters over from the origin, which is exactly the 50 centimeter mark. So you see, that does work. That fits our everyday life experience definition of center of mass. It turns out if you actually have to do it with discrete things, then X center of mass would be the integral of X dm over the integral dm, and Y cm would be the integral of Y dm over the integral dm. You can see examples of these on my YouTube channel already. You can also see a train car example. that's really neat. You'll see like 3 versions of the train car example. One's using conservation of momentum, another one's using center of mass. I definitely recommend you look at those. I don't think I have them linked on your Canvas page yet, but they will be. And our time is up. So you guys are free to go. Remember, we're not going to have lab this week, but you're free to go. And I'll wait for the last person to leave before, so you can ask me questions.
I just wanted to check about my lab mastering homework due dates for chapter 9, since they haven't been updated yet. Is that going to be?
Yeah,
this
I'm leaving them
weekend?
that date. I checked them again today, and it looks like I've got them set way far back. Like we're about to finish chapter 9. We're actually going to finish chapter 9 Monday, and it's actually set, I think, to not this coming Wednesday, but the Wednesday after it, and that's fine. I would definitely try to do it before you take the test that covers chapter 9, but that's not the midterm, so you're golden on that.
Okay, so no, there's no chapter 9 on the midterm.
No, the chapters are 1 through 8 on the midterm. Chapter 7 problems is due tonight. Chapter 7 concepts were due Sunday. Chapter 8 concepts will be due Sunday, and chapter 8 problems will be due next Wednesday. So that actually makes the chapter 9 another week beyond that. So it's even a week farther than I thought.
Okay, and then the midterm is on Monday, so we would finish chapter 9 on Wednesday.
Yeah, that's right. I forgot about that. So yeah, we'll finish it on Wednesday. Thanks for correcting me on that.
Yeah, no problem. And then with the practice midterm as well, I didn't see a time like in the prompts from the lockdown browser to show our sheets to the camera or anything for like, here's the equation sheet and here's my blank paper. Do you want us
Yeah,
to
I didn't put all those
link to
instructions in
it?
there. The main thing I was wanting you to do is to get a chance to, 1, see the correct answers to the trial that you took, and then 2, to make sure you download your lockdown browser. The instructions you'll get to see when you actually take the test. I might even
Okay.
send them out as an email so you'll know.
Great. That's what I wanted to check, was specific instructions for the actual midterm. Thank you.
No problem, Abby. And Aaron, the midterm we moved to Monday. Now what that means is the class starts at 5:45, but I've given you a full 2 hours. So I'm letting you start as early as 5, but you only have 2 hours, or you can start right on time at 5:45, but you will be stopped at 7:45 because you get 2 hours. Now that means if you come in late, if you start taking your test at 5:50, then you're only going to get 1 hour and 55 minutes, and that's on you. So you got to make sure that you can either stay late or come early, and that you can work the full 2 hours. If you don't, that's, like I said, that's just your loss because you didn't follow instructions or whatever. Not to sound too mean, but just warning my folks, my peeps. Anybody else have any questions?
When we're taking the midterm, is the Zoom class going to be on and we're also going to be in lockdown browser?
No, there's a video component where they have people that watch you for suspicious behavior, and I can also chime in at any point and look and check what y'all are doing. So like if I get a call from, some disgruntled roommate of one of yours that says, hey, such and such is cheating, then I could actually look at such and such and taking the test in real time. So there's always that scenario. So dress professionally. Don't come in your jammy jams or your undergarments or whatever, and just make sure you don't do anything cheating wise.
All right, so it's just that the test is gonna be open at 5.
Yes, and you're going to start it at whatever time you can. Like I said, if you can't start it right at 5, you can start at 5:30 and then work till 7:30. It's going to be timed for 2 hours.
Gotcha.
So it's more so like it's real time. It's not like, so if I wanted to take it on Sunday, I couldn't take it early.
No, if you got to take it at the actual time, because everybody's taking the same test. If you have a class that conflicts with it, so you can't start early or finish late, then you show me your schedule and it shows that, then I can actually make you a separate test and let you take it at a separate time. But that makes, again, a whole nother test.
Okay.
Aaron, Gavin, anybody else have any questions? Hassan, Jarrett, Gabby? No, that's Abby, sorry.
Have a good night.
Hey, you too. Thank you all for coming, and I will have this stuff posted as soon as I can. Thanks for coming.